I want to continue my discussion of fluid statics now by turning to applications of the hydrostatic pressure equation to manometers and barometers. Firstly, barometers are devices which have long been used to measure atmospheric pressure, and typically we do this by measuring the height of a column of a fluid, which is typically mercury. So a mercury barometer is shown here, and we can relate the height of the mercury column to atmospheric pressure by applying hydrostatics. So, for example, at this point here, the pressure there is the same at those 2 points because the horizontal level is the same, and remember the pressure on any horizontal plane is constant. So therefore, the pressure at this point is the same as the pressure here, which is atmospheric pressure, and the pressure here is the pressure due to the height of this column of mercury, which is specific weight of mercury times h, plus the vapor pressure of the mercury above here. And the vapor pressure of mercury is very low, so we can effectively neglect it. So basically the equation is that atmospheric pressure is equal to the specific weight of mercury times the height of the fluid column. To show what that would be for typical values, we recognize that the specific gravity of mercury is about 13.6. In other words, it's 13.6 times heavier than water. So the density of mercury is 13.6 times the density of water, which is about 1,000 kilograms per cubic meter, which is 13,600 kilograms per cubic meter. Or the specific weight of mercury is the density times acceleration due to gravity, which is about 133 times 10 cubed newtons per cubic meter, or 133 kilonewtons per cubic meter. Standard atmospheric pressure is approximately 101 kilopascals absolute. So the height of the mercury column is atmospheric pressure divided by the specific weight of mercury, which is therefore 101 times 10 cubed, divided by 133 times 10 cubed is 0.759 meters, or approximately 760 millimeters. And if we did the corresponding calculation, assuming that this column here was water, the corresponding height would be 34 feet, which is obviously very impractical, which is why we typically use mercury as the fluid in a barometer. And to illustrate the difference between the two, the pressure due to a column of 760 millimeters looks like this, is approximately 34 feet tall. Manometers are devices which are used to measure pressures of fluids by observing the height of fluid columns. Consider, for example, I have a pipe or a vessel here, and I'm interested in the pressure in this pipe, which we'll denote by PA. It's connected to a manometer, and where the manometer contains some different fluid, the manometer fluid, whose specific weight is gamma 2. Now, to analyze cases where we have columns of different densities, let's consider a simplified example here. So here I have an open column here, which is filled with gasoline at the top, and it's overlaying an immiscible fluid, water, so the two fluids don't mix. What is the pressure at the bottom of these two columns? Well, to find that, first of all, we apply hydrostatics to the gasoline from this point to this point, and the difference in pressure between these 2 points, P1 minus P0, is just the pressure which is due to this column of gasoline, which is equal to minus gamma g times the height difference, Z1 minus Z2. Similarly, I apply hydrostatics to the water column from the interface here to the bottom of the water column, and the equation there is the difference in pressure, P2 minus P1, is minus gamma water times the height difference, Z2 minus Z1. Next, I add these two equations together, and when I do that, the pressure at the interface, P1, cancels out and leaves me with P2 minus P0 is equal to minus gamma gasoline Z1 minus Z0 minus gamma water Z2 minus Z1. Or rearranging the pressure at the bottom, P2 is equal to the pressure at the top, P0, plus the pressures due to the two columns of liquids, gamma G times Z0 minus Z1 plus gamma water Z1 minus Z2. In other words, very simply, all we do is add the pressures due to each column of fluid when we have different fluids. So in this example, if the specific gravity of gasoline is 0.68, I'll leave you to do these calculations as an example. The pressure at the bottom here, P2, is 6.31 psi. In other words, pounds per square inch gauge above atmospheric pressure. If we have a single fluid, the equation is even more simple, and in this case, the pressure here is just equal to the pressure due to the column of fluid here, which is gamma 1 times H1, plus the pressure at the open surface here, which is atmospheric pressure. For high pressures or gases, we typically use a U-tube manometer, like on the previous slide, which looks like this. And all of these manometer problems can be solved very simply by following a few general suggestions or rules that I'll give here. And the suggestion is this: start at one end and write the pressure there, for example, in this case, PA, and then work your way through all of these different fluids to the other end, where we equate the pressures due to each fluid column, and we add the pressure if the next meniscus is higher, subtract the pressure if the next meniscus is lower, and then finally add the pressure at the other end. And if you follow these simple rules, you can solve any complex manometer problem. So in this case, we have PA, write the pressure at the one end, PA, and then go from here to this meniscus. This meniscus here is lower than this, so it's going to be negative, and the hydrostatic pressure due to each column is just the specific weight multiplied by the height difference. So it's minus gamma 1 times H1. Next, we go through the blue fluid here, the manometer fluid, to here, passing straight through the point 3, because that's irrelevant. This meniscus is higher than this, so it's positive gamma 2 times the height difference, which is H2. And then finally, adding the pressure at the open end here, which is atmospheric pressure. So this is the equation that would apply to that particular example. Now let me do some numerical problems. So in this case, we have a closed tank which is filled with water. Above here, we have air, and the pressure gauge is reading 7 psi. If the specific weight of the water is 62.4 pounds per cubic foot, the height h of the water column is most nearly which of these alternatives? So here's the solution. We apply that simple rule that I just applied. So start from this point and write the pressure there, P air. Go through the water column from here up to here, and this meniscus is higher than the free surface here, so that is equal to gamma times the height difference, which is h minus 2, and then add the pressure at the free surface there, which is atmospheric pressure. So this is our equation. So rearranging, in this case, we want to solve this for h, so we have h is equal to 2 plus p air over gamma. The pressure of the air here we're given is 7 pounds per square inch, and convert that to pounds per square foot, multiply by 144. So therefore h is equal to 2 plus 1008 divided by 62.4 is equal to 18.2 feet. So the closest answer is C, 18.2 feet. Another example, a little bit more complicated. The closed tank contains a liquid with a vapor above it. The liquid density here is 800 kilograms per cubic meter, and the vapor density is negligible. The pressure at the top of the liquid in the tank is 120 kilopascals absolute, atmospheric pressure is 101 kilopascals, specific gravity is given, and density of water is given. Question is, the reading H here on the mercury manometer is most nearly which of these alternatives? So again, the solution, just follow those simple rules that I just gave you. Start at this point here, and the pressure at this point, which we'll call PV, is equal to, so first we go through the liquid here, all the way through here to here, just go through the continuous liquid, and this meniscus is lower than this meniscus, so it's going to be negative, and the hydrostatic pressure is minus gamma L, the specific weight of the liquid, multiplied by this height difference, which is 1 meter. Then we go through the mercury column from here to here. This meniscus is higher, so it's going to be positive, and the hydrostatic pressure is gamma mercury, gamma Hg, times the height h, and then finally add on the atmospheric pressure at the free end. So rearranging this equation for h, which is what we're trying to find, we get this, and remembering that the specific weight, gamma of mercury, is equal to the specific gravity, Sg, multiplied by the density, Hg, we have this equation, and now we can plug in the numbers. The pressure here is 120 kilopascals, 120 times 10 cubed, plus etc., and plugging in the numbers, the answer is H is equal to 0.201 meters, or 201 millimeters. So the best answer is D, 200 millimeters. Notice in this problem that I worked this through in absolute pressures, because we gave the atmospheric pressure here as an absolute pressure. You can work these problems at either gauge pressures or absolute pressures. You will get the same answer. However, you must be careful not to mix the two. Work only in absolute pressures or only in gauge pressures. The final example, we have an inverted U-tube manometer containing an oil which has a specific gravity of 0.9. The pressure difference between the two pipes here, A and B, is minus 5 kilopascals, and the specific weight of water is 9,800 newtons per cubic meter. The reading H here, where H is the difference between these two levels, is most nearly which of these alternatives? So again, follow the same procedure. We start here at the left-hand side, so I write the pressure here as PA, then go through here to this meniscus, okay? So that is equal to the pressure due to this column of fluid here, which is positive because this meniscus is higher, specific weight times the height, which is 0.2. Then I go through the oil here, from here to here. This meniscus is lower, so it's going to be negative, and the pressure is gamma O, specific weight of the oil, times height, times H. Finally, I go from here to here. Again, this meniscus is lower, so it's going to be negative here, specific weight of the water times 0.3, and finally, plus the pressure at the other end, which is PB. So rearranging, I get the pressure difference, PA minus PB, is given by this expression. And again, I'm interested here in the manometer reading H, which is equal to this. So rearranging, and I get this expression. Plugging in the numbers, PA minus PB is equal to, we're given minus 5 kilopascals, minus 5 times 10 cubed, plus the specific weight of water, which is 9,800 newtons per cubic meter, multiplied by the height, which is 0.1, and the answer is 0.456 meters, or 456 millimeters. So the closest answer is A, which is 460 millimeters.